We can define circular motion as the movement of an object along the circumference of a circle or rotation along a circular path. This movement can be uniform with constant angular rate of rotation and constant speed, or it can be non-uniform with a changing rate of rotation. The rotation around a fixed axis of a three-dimensional body involves circular motion of its parts. The equation of motion describes the movement of the center of mass of a body. There are many examples of circular motion, such as a satellite orbiting the Earth at a constant height, a ceiling fan's blades rotating, a stone which is tied to a rope and is being swung in circles, a car turning through a curve in a racetrack, an electron moving perpendicular to a uniform magnetic field, and a gear turning inside a mechanism. Since the object's velocity vector is constantly changing direction, the moving object is undergoing acceleration by a centripetal force in the direction of the center of rotation. Without this acceleration, the object would move in a straight line, according to Newton's laws of motion. There are three aspects that will be of our interest when we analyze circular motion. These three quantities are speed, acceleration, and force. The speed of an object moving in a circle is given by the following equation. Average speed equals distance over time equals 2 times speed times radius over time. While the acceleration of an object moving in a circle can be determined by these two formulas. Acceleration equals speed squared over radius. Acceleration equals 4 times p squared times radius over time squared. The net force acting upon an object moving in circular motion is directed inwards. While there may be more than one force acting upon the object, the vector sum of all of them should add up to the net force. In general, the inward force is larger than the outward force, such that the outward force cancels and the unbalanced force is in the direction of the center of the circle. The net force is related to the acceleration of the object and is thus given by the following three equations. The net force is equal mass times acceleration. The net force is equal mass times square speed over radius. The net force is equal mass times 4 times p squared times radius over time squared. Now that we have this information, we can start with our experiment. Description. The experiment consists of provoking a bicycle wheels to spin. When the wheel is spinning, you are going to prove the given formulas. In order to check the formulas, I am going to use Tracker. Tracker is a software which allows us to analyze physical processes by filming the case. Our objective is to check the given formulas via Tracker. Hypothesis. I am sure that the result will be almost the same or that there will be changes in the decimals of the answer, but no big difference in both results. For this simple experiment, we are going to use a bicycle, a camera, and a computer with Tracker. By spinning the wheel and interpreting the obtained data in Tracker, we will be able to determine the following results. First of all, we obtain the radius of the wheel, which is 35 centimeters. Next, we need to record our spinning bicycle wheel. We upload our video to Tracker. In Tracker, we capture our data, and with this data we can see that our period in which the wheel goes around is 0.73 seconds. Now that we have our period, we can solve our formula, which is average speed equals 2 times p times radius over period. The result is 3.012 meters over seconds. can obtain our acceleration with the given formula, which gives us a result of 25.93 meters over second square. And last but not least, here is our net force formula, which gives us a result of 33.71 newtons. Now, thanks to this little experiment and these formulas, we could determine the average speed of the bike, the acceleration, and the net force. Finally, we can conclude that our bicycle is not moving so fast and that our formulas were very useful. Thank you very much for your attention, and I hope you have a wonderful day.